All right, so does anyone have any concerns or questions that we should talk about? Okay, that's no. Um, all right, so would you guys like to recap what we were talking about yesterday and maybe talk about some new material?
Yes,
Yep.
please.
All right. So let me share my screen. Let me get rid of that. And take a look at this. All right, so this is the first PowerPoint plate for chemical kinetics that we were talking about yesterday. And these are some of the big five factors that you want to take a look at when you're trying to get a handle on or understand better how chemical reactions take place and at what speed that they occur. So we mentioned that, yeah. Oh, let's see, I have to let in some people who are late. Admit all. All right. Okay, sorry about that. So these were the five topics that we were going to take a look at. Number one really is a no-brainer, the nature of the reaction and the reactants. 2, 3, and 4, that's where we're gonna look at most of our mathematical models and try to understand conceptually how reactants come together and form products and how that affects the rate of the reaction, how temperature affects it, and catalysts. And if we can mathematically model these three criterion, this will give us a good understanding of kinetics, and it also give us a good understanding of how to use mathematical models um, along with those concepts at getting a deeper and richer understanding of what's going on. Now, surface area, we just mentioned physical state, and we're not going to mathematically model that at all. All right, so the first equation that we looked at was this ratio of the change in the number of molecules with time. We kind of equated that to miles per hour or meters per second, which is a rate. So it kind of makes sense so far. We then said, well, in the laboratory, we don't really measure moles directly. What we keep track of is concentration and how that changes in time. But that's not a big deal. That's just dividing by the volume, which is constant, usually constant in any reaction that takes place under um, atmospheric conditions in the laboratory. So that was just a little change of our equations. Then we noted from this experimental data on concentration with time, how you can calculate average rates for those time intervals. And we also noted that as the time goes on and the reaction proceeds, the concentration decreases of our reactants, which makes sense. And also we saw a decrease in the rate of the reaction as time goes on. And that is not always the case, but is often the case. Then we said, well, what if we're interested in initial rates, not average rates over a time period? How could we work that in, and how does that connect to the calculus? So we discussed the slope of the tangent line to the curve argument, and how it has the same units of rate and it's an instantaneous because it approximates the point where delta t approaches zero. So we talked about that a little bit. We introduced this generalized rate equation that applies to any reaction. So this generalized reaction that we looked at has two reactants and two products, but there's no reason why we can't have more or less. The equation down here still applies, and we saw that for example, if we wanted to talk about the rate of consumption of, say, A, that would be delta concentration of A over delta T. We can identify that in this relationship that's provided. And we also note that if we want to relate that rate of consumption of A to any rates of consumption of any of the other reactants, or the rate of production of any of the products, in this case C and D, or to the overall rate of the reaction, then we would need to scale that by the stoichiometric coefficient. Then we said, okay, that's all fine and good. We have to study our definitions and understand what that generalized equation is telling us and how we can relate those rates to each other. Then we looked at a specific example of this reaction where we have 2HI going to H2 gas and I2 gas. And so we just made the comment that that it makes sense that if A represents the reactant, and I want to look at the rate of consumption of that reactant, which is in this case HI, to the other rates in the equation, namely the rate of production of H2, or maybe the rate of production of I2. That could be, I'm sorry, the B in this generalized equation, that refers to another reactant. So I would have to pick C and D for products. And I know that that's different because it has a little negative sign. And we had commented that the reactants have negative signs because in time, their concentration's decreasing. So the delta is going to give us a negative. Delta A and delta B is going to give us a negative if they're reactants. So we need to get rid of that negative sign to relate to the other rates. But anyway, back to what I was saying, if this generalized equation can be applied to this reaction, and we do it here, then it makes sense that if I have a rate of consumption of HI, I'm going to have to scale it or divide it by 2 to equate it to the other rates, which happen to be both production, by a factor of 2, because I can see that I'm going to need 2 HIs for every 1 H2 that's produced and every 1 I2 that's produced. So its rate of consumption is twice as fast. So if I'm going to relate that to the other guys, then I better scale it by that factor too. Any questions so far? All right, so this is all what we talked about yesterday. And I think that was pretty much where we left off, if is that right?
Yes.
Okay. All right, so now we're going to move on to a related topic, which is called the rate law. Now, the rate law centers on trying to mathematically model the effect of concentration on rate. So if we go back to that first slide, that would be category 2. How does the reaction concentration affect the overall rate of a reaction? So now we're going to get into that here with this plate. So what we want to do is derive what's called a rate law. And it talks about the rate law on this plate. And it says, for example, take a look at this reaction here. Okay. Now, so far in our discussion, we're only considering initial rates. So for initial rates, what the reaction mixture looks like is it has all initial concentrations of reactants only. So there isn't any products, okay? And we want to find some sort of a mathematical function that's going to tell us how rate changes with concentration. So it's got to be proportional to, that's a proportional sign. It's kind of sloppy. Sorry about that. But I think you know what I mean. So that's proportional to the concentrations of the reactants. That's what the rate would be. So if I have some reaction A going to B, then the rate law is going to be proportional to that concentration A. And I don't know if it's going to be a linear type of relationship or a quadratic. So I can put that dependency as another unknown, such as X. But I think you can see that, and it's important to notice this, that as soon as I write down the reaction, whatever it is, I have defined my reactants and I've defined my products. So when I talk about the rate of that reaction or the rate law, then I'm going to want to identify the reactants and know that that rate has some connection to the concentration of the reactants, not the products. So here I look at a specific reaction at 25 degrees Celsius. I have ammonium reacting with nitrite to form some products. So as soon as I identify that reaction, I know the form of the rate law. Rate is going to be proportional to ammonium to some power, I'll call that X, and nitrite to some power, which they call Y. Now, if I keep everything constant experimentally, and the only thing that I vary is the concentrations of the reactants, then I can make what's called a proportionality constant and change the proportionality into an equals. Once I realize this, then I've defined the form of my rate law. So this is the rate law for this reaction right here. Now, of course, I have a few unknowns in there. I have this proportionality constant K, which I don't know, and I have this X and Y factor, which I don't know. And the only way that you can know these is by doing lots of experiments and analyzing your experimental data. And then you can go back and propose the rate law and define what K is in terms of a number and define what X and Y, what both of them are in terms of numbers. And so that's what we're going to do. We're going to take a look at how you can use experimental data to come up with this mathematical expression called the rate law. And the rate law will allow you not only to model the experiments that you have in your table or the experiments that have been done, this rate law will work for experiments that aren't done yet or ones that you haven't thought about. It's a law that will work as long as the only thing that you change in any experiment are the concentrations. Is that sound pretty reasonable?
Yeah.
Can we do an example?
Yeah, we're going to do some examples in just a second, but before we get to that, I just wanted to ask any questions in a general nature. Um, are we good so far with this?
Yes.
Okay.
Yep.
All right. Now
Yep.
here's the example that you're asking. And we'll get to do more examples. And you know what? There's a lot of examples in your homework. And as soon as we're done this concept, we can go right to your homework and take a look at them like we did yesterday for the first few and show how that related to what we were talking about. So anyway, if there are any questions or you want to hear more on some topic right now, then by all means, just holler out and I'll try to accommodate you. All right, so now we're back to this reaction again that we were considering, the ammonium nitrate reaction. And someone has gone to the lab and they got some experimental data for us. They did 6 experiments here. 1, 2, 3, 4, 5, 6. And in each of these experiments, they use certain concentrations of ammonium and certain concentrations of nitrite. And then they calculated in some way the rate of the reaction. Now, we don't know the details of the experiment. The first experiment that you guys are going to get to do in lab allows you to calculate the rate of reactions. And so you'll see how that can be done. But essentially, in order to calculate a rate of a reaction, this last column over here, experimentally, you just need to track the changes of the concentration versus time. And you can do that. I don't know if you guys ever did a Beer's Law experiment where you shine light through a sample and you see how much it absorbs because there's one of the reactants or products in that sample that interacts with light. So you can follow its concentration in time. And so it could have been one of those. Or maybe you titrated a sample as time goes on and experimentally determine how the concentration is changing. They don't tell you, but you don't need to know how these rates are calculated. You just need to know that they were calculated and they have the usual unit, which is molarity per second. Okay. So the first experiment, we see that ammonium here, that has a 0.01 molar concentration, whereas the nitrite has a 0.2 molar. In the second experiment, what happens to the ammonium concentration?
It goes up.
Yeah, it goes up by twice as much. It doubles. How about the nitrite?
Stays the same.
Yeah, it's the same. So this is a common scientific method where when you want to deduce experimentally the effect of something, you make sure that everything else is held fixed. So by analyzing or comparing experiments 1 with 2, I'm essentially analyzing the effect that the concentration changes of ammonium has on the rate. What happens to the rate when I double the concentration of ammonium, keeping nitrite fixed?
It doubles?
It doubles, man. So that is a clue. That's a mathematical clue of how to form our rate law. What we say, that's a first order effect. The rate depends on the concentration of ammonium to the 1 power. Okay, so you double its concentration, the rate doubles. That's a linear or a first order effect. Now, check out the other experiments. Now, I've picked experiments 5 and 6 to compare next. Why do you think I picked that one to compare next?
It's opposite of 1 and 2.
Yes, and now I want to find the dependence of nitrite on the rate, leaving the other guy, which in this case ammonium, fixed. So by comparing experiments 5 and 6, ammonium is held fixed, and this time nitrites doubled in concentration. What happens over here?
Quadruples.
Yeah, the rate goes up by 4 times. Now that's called a second order effect or a quadratic effect. It's nonlinear, and we see this experimentally. Now, how can this effect be translated in a mathematical formula? How can you use this to make the rate law to predict the results for any experiment that you have and any other one that you might do? We're going to show you how to do that. Again, we note what happens. And now we say, well, I know that the rate is going to be proportional to the concentration of ammonium to the 1 power, because it's a first order effect. And I know that the rate is going to be proportional to nitrate to the 2nd power, because it's a second order effect. So my rate law now is defined, at least in terms of X and Y. X is going to be 1 and Y is going to be 2. And K still needs to be determined. But before we go on and talk about K, let's go back and prove that that's true when we propose this rate law. So I want to insert a new slide. All right. So let's show this. Let's say I have experiment 1 with rate 1. And now that equals some K, which doesn't change because I didn't change anything in the experiments, not the temperature, not the pressure, not the identity of the reactants. Everything else is the same. I didn't add a catalyst. I didn't change the surface area. And I have the concentration of ammonium. And that's in experiment 1. And I have the concentration of nitrite in experiment 1 to the 2nd power. Then I do this. Let's show how the math will predict what we found in that table. I have another experiment 2. Again, K is going to be the same. And this time, this is going to be 2. All right. Now, what's the difference between experiment 1 and experiment 2? In experiment 2, ammonium 2 is 2 times the concentration of ammonium in 1. All right. So I can make that substitution right here. Okay. So I say, all right, equals K times 2 times the concentration of ammonium. But now this is going to be a 1, 2 times 1, and this guy's the same. So this equals 2 times K ammonium 1 times nitrite which is the same, since I didn't change those ones. So I should probably put that up here too. NO2 minus in 1 equals NO2 minus in 2. So they're the same. And now I can see that this rate for 2 equals, this is rate 1, 2 times rate 1. So do you see how that rate law shows what we see experimentally for a doubling of ammonium? Does everyone see that?
I see that, but why did you? How are the nitrites the same in both rates?
Oh, remember back in the table, we picked experiment 1 and 2,
Mm-hmm.
and in
Oh, okay.
experiment 1 and 2, we made sure that that one didn't change.
Oh, got you. Okay, I thought you were just doing an example. That's why.
Yeah, no. And so,
It's going off
now,
of that.
so do you want to do the same thing, but this time we'll do it with nitrite and see what happens when we double that?
Yeah.
All right. Let's do that one real quick. Now, that was like 5 and 6, I think. So I have the rate of 5 equals K times ammonium in 5, nitrite in 5, and then R6 equals the same form. You see, we get the same form because we're looking at the same reaction. Oh, this is 6. All right. Now, what's the difference between 5 and 6? Well, ammonium in 5 is the same, so that's not it. It's the nitrite. So the nitrite in 6 equals 2 times the nitrite in 5. So I can make this substitution here and this one. So when I do that, I'm going to do K is the same. Ammonium is the same as 5, so this is R6. And nitrite, oh, sorry, I forgot to put the 2 up here. That's because we saw that nitrite was a second order effect. I can't forget that. And so now I'm going to make this substitution. And I'm going to put 2 times NO2 minus in 5, but that whole thing has to be squared. And so again, this equals K ammonium 2 squared is 4. And then we get NO2 concentration 5 squared. So now I think you can see that 4 comes out. K ammonium nitrite squared, which equals 4 times R1. Not R1, sorry, R5. So in effect, the rate quadrupled just like we saw it back here in the table. So I think that that should prove to you that these rate laws predict not only what we have in the table, but other reactions that we haven't even done yet. We just need to put in the concentration. Once we have the rate law, once we have this rate law, then you only need to put in the concentrations, those values, and for nitrite, you have to square it and multiply it by K to find the rate of the reaction. Now, we haven't talked about K yet. That's next. But I just want to,
Oh, sorry. I was gonna say, does the 4 go in the front of K because the entire reaction is quadrupled? Or why does that
oh,
go
I
to the,
moved, yeah, thanks for asking. I moved that out to the front, just like I moved the 2 out to the front over here, just because I was trying to see how that rate 2 in this case related to rate 1. So I needed to identify this whole bit here with rate 1.
okay, I see.
So the 2 was left over, and it was the same thing with this guy. I was trying to find out how would I predict the rate in experiment 6 would change compared to experiment 5. So I was trying to group the terms so they would look the same as the rate for experiment 5. So then I can identify that with rate 5.
Okay, and so if the question was reversed and it was asking how, like, if you were trying to write things in terms of 6,
Mhm.
would you have just done like a 4th out front or something and put 6s as the subs? Or do you always go to the smaller experiment?
Um, I think mathematically the order doesn't matter. You can do it either way. But let's take a look at what you're saying. But let's do it for some experiment 10 or something like that. I don't know.
Okay.
So experiment 10, let's say in experiment 10, we tripled the nitrite concentration and left the ammonium the same. How would that change stuff? So for 10, it's going to be K times the concentration of ammonium in 10, which we didn't change, times the concentration of nitrite in 10, which we did change. We're going to triple that compared to case 5. Okay. How is that going to change the rate of 10 compared to 5? I think that's what you want to know, right?
Yeah.
We're going to use the equation to predict the change now. All right, so we can do that. We'll just bring this down. This ammonium in 10 is the same as 5, so I can replace that with a 5 subscript because I didn't change that. And now I want to replace the concentration in 10 with the concentration in 5. But I want to 3 times that amount, and this whole thing is squared. Okay. So now I'm running out of room. Let's go up here with this. So I could rewrite K ammonium plus and 5 times 3 squared is 9. And I'll put that 9 out here. And then I'll have this other part, NO2 minus squared in 5, which is the rate for 5. So I see that the rate for 10 is going to equal 9 times the rate for 5.
Okay, I understand.
Awesome. Yeah, so it goes both ways. Once you have the rate law, you can predict future rates given changes. And also you're going to need to, well, take experimental data and come up with the rate law using that experimental data, just like we did. All right. Now, we didn't talk too much about that K. So let's go back and talk about that, because that constant can be determined from experimental data too. And that's the way you have to do it. Anyway, the proportionality constant K is referred to as the rate constant. And that's the rate constant that goes with the rate law. And the rate law is the law that tells you how changes of reactant concentration affect the overall rate of a reaction. Now, the units of the rate law are kind of funky. I don't think in all your scientific career thus far, you've ever had a constant that has units that change. And those units depend on the overall order of the rate law that it's in. So what's the overall order mean? Okay, well, I know from analyzing that data that the rate law is first order in ammonium and second order in nitrite. So the overall order is 1 plus 2 equals 3. That's the overall order. And essentially what that tells you is how many molarities are expected to multiply that K, right? Because the units of concentration of ammonium is molarity. And if I have it to the 1 power, that's 1 molarity. The units of concentration of nitrate are also molarity. And if I square that, that's molarity squared. So essentially, this is telling you it's third order. It's telling you that after you multiply all the concentration dependencies, that you're going to have a unit of molarity to the third. And so what they did was they said, well, the rate law, K, its units are going to change so that the rate in the rate law, this rate, always comes out with units of molarities per second. So if it's third order, I have too many molarities there, right? So K, therefore, for this instance, the units of K are going to have to take 2 of those molarities away. And it's also going to have to give me per second. So for a third order reaction that gives a rate law that has an overall third order, the units of K must be 1 over molarity squared times seconds. Any questions on that? Good. All right. And that also implies that if the rate law is 0th order, which means it doesn't have any concentration dependency. So R equals K to something to the 0th power, that's 1. Then what's the units of K? What does that have to be? If rate always has to be in molarities per second. Anybody?
Second.
Yeah, it's got to be in molarities per second. So this is for a 0th order overall, whereas this was a 3rd order overall. And a 1st order overall, rate equals K times some, let's say, reactant to the 1st power. The units of this K are just going to be 1/seconds, because a molarity is going to come from the concentration part. And that's going to give me my rate again in molarities per second. Are you guys getting the hang of this?
I'm confused with the 0 order one. So why is it 0 plus 1?
I don't see where you're getting the +1. This is just as, I'm just talking about an overall 0th order. So say I had analyzed this reaction back here, again, the ammonium nitrate, and it turns out that both of them are 0th order, which means no matter what the concentration is, as long as there's some reactants, the reaction rate is the same. It just chugs along at the same speed. It doesn't change if I increase or decrease any of the concentrations, as long as there's some there. That's called the 0th order effect. And so I would write that rate law for 0th order as ammonium to the 0th and nitrite to the 0th, but anything to the 0 is what?
One.
Yeah, so they're just 1. So that means the rate for a 0th order reaction equals K.
Oh, okay. I see.
Yeah, thanks for asking that, though. I'm sure that was not clear.
I couldn't see what on the right side of the screen where the K over molarity over seconds, and then there's like a 0 and like a little
Oh,
plus
gee,
something.
yeah.
Uh,
Yeah, sorry about that. But I'm glad you asked anyway.
yeah, thank you.
Uh-huh. All righty. Any other questions on that? We're going to look at this a little bit more when we start doing the problems. And because we're going to have to also determine what K is. Now, once you have the form of the rate law, then you can go back and use the experimental data to determine K, because using this method, each of those reactions or experiments, I should say, each experiment has the same form of the rate law. You just have to change the concentrations of the reactants in the rate law. So then you just get to 2 equations and 2 unknowns and solve your K. So I'd like to do that in a little bit. Here, it kind of helps you visually see what it means to have these different 0th, 1st, and 2nd order effects on rate. So it's a nice picture, and hopefully it'll help you understand a little better about what's going on. So these rate laws, remember, they're going to take the form of the reaction. So if it's just a unimolecular reaction, let's say A going to B, we'll just make it really simple. Then the form of the rate law is right here. And if that power dependency turns out to be 0, which means it doesn't have any effect, then it shows you how the concentration of A is going to change in time. It looks like this line right here with a constant slope, downward slope. So it just chugs along at a constant rate because the rate is associated with the change in the concentration over the change in time. That's the slope. And you see that that's a constant slope, change in y over change in x. And that's what it should be because it's associated with the rate. The rate should be constant because it equals a constant, and it is. First order, you see it kind of tails a little bit. And then second order, it bends even a little bit more here. As the time goes on, the concentration has more of an effect on the rate. Oh, on the next plot, we have the rate plotted versus the concentration for the different orders. So again, let's take a look at 0th order. There's our 0th order rate equation. We see that the rate equals K because anything to the 0th power is 1. So the rate should be constant no matter what the concentration is. And that's what you see. The concentration could be 0.2, it could be 0.8. The rate is still going to be around 0.015 molarities per second. It's constant. As opposed to first order. As the concentration increases for a first order effect, the rate increases with a constant slope. For second order, you see that the rate kind of bellies out here at the bottom, but then catches up to the first order by the time the concentration becomes 1. And then after that, it's going to go at a faster rate than the first order. All righty. Any questions on that? Okay. Now, there is a way to determine the exponents in a rate law, the x and the y, and also the k, purely mathematically and using experiment. So we can see that, and back here we took a look at it, what happens when you double the concentration of a reactant that has a second order effect. We did that right here. Well, the rate increases by 4 times. And we proved that with the math. And a lot of people in your textbook and a lot of textbooks, they just use the eyeball method. So pretty much you're memorizing this. So you get used to saying, okay, if I double the concentration and the rate doubles, that's a first order. If I double the concentration and the rate goes up by 4, then it's second order. And that's kind of called the eyeball method. But you can use the equations because each one of these reactants produces a different equation for that specific experiment. But the form of the equation is always going to be the same once you determine what k and x and y, the exponents are. So another way to do that from experiment to find the the rate laws is just to make ratios of those generalized rate equations and divide them out for one experiment to another. And that's what this plate talks about. You can just use ratio of the rate equations. So what this says is, say you have some reaction, simple reaction, one reactant. So as soon as I see that, I see the form of the rate law is going to be something like this. A to the X. I don't know anything else. That's the form. Now, if I have experiments, then I can start taking the ratio of those experiments. Like here, this is experiment 2, and I divide it by experiment 1. The K's drop out, and so I get a ratio of the rate of 2 over 1, which I just plug in numbers from the table. And I also have their associated concentrations in 2 and 1. And I plug those numbers. So you see, you only have one equation and one unknown, n. You just solve it. And so that's another way that you can figure out what order your rate law must have using experimental data. Okay, and so it talks about that a little bit more on this plate. And I think it asks you to do an example in the next one. Yeah. So here you're probably waiting, okay, let's see an example of how to do this. And so this plate talks about that. Here I have some reaction that I want to find the rate law for. I know the form as soon as I see it. As soon as I see that, I see, oh, there's only one reactant. So the form is going to be rate equals K times the concentration to some power. And now I look at my experiments. So I see from experiment 1 and 2, the concentration doubled. What happens to the rate?
It almost quadruples.
Yeah. Yep. Right, you guys. So that's 4 times. So what order is X?
Second order.
Yeah, it's second order. But how can we use those ratio of the rate laws to determine that? That's what's on the next slide. Say you couldn't see this, like if they gave you experimental data where this wasn't exactly doubled, what if it was 1.5 times, and this changed by, I don't know, some fractional amount. It's harder to do in your head, right? Well, you don't have to, because you can just take the form of the rate law for each one of those experiments and divide them out. And so that's what I did. I just picked here rate 2 and 3, but you can pick any one. You put in the rate of 2 divided by the rate of 3, and you put in the concentration in 2 divided by the concentration in 3, all to this n power, and then solve for n. So how do you do that? Well, this ratio equals this number, and 0.2 divided by 0.3 equals 0.6. So we reduce that equation to here, but how do I solve for n? To do that, we need to employ a law of logs. So if I take the ln or log, it doesn't matter. There's a law that says that log of x to the y equals y times the log of x. It's one of the law of logs. You can even plug in numbers like I don't care what you plug in, 2.5 could be X and 3.7 could be Y. You can go ahead and do the log, see what number you get, and then do it again over here, and you should get the same number, which proves this law. But anyway, you can see that I can solve then for any exponent using this, because the Y goes from being an exponent to being down here, and it makes it easier to solve. So how do I employ that here? I take the log of 0.6666 to the n, that equals n times the log of 0.6666. I take the log of the other side, the log of 0.445 should equal that exponent n to the log of 0.666. So n equals this ratio. And what do you know? It gives us the right answer, just like we got from the eyeball method. So you should practice doing this, and you'll have practice when you look at the homework. Any questions on that? All right, this last part talks about how you can solve for K, the rate constant. And it uses that data. And we kind of skipped over it so far. But once you have the rate law by analyzing the experiment, in this case, it's second order. So I know that this is a 2 up here, second order. Then I can use any one of these experiments to calculate K. And oftentimes they use each one. So you would get a K for K1, experiment 2, 3, and 4, and then take the average. And they all come out pretty close. So what I would do then is I would say, here's my form of the rate law. So I would put in the rate, which is in this case 0.02. That has to equal K times the concentration of 0.10 squared. And so I solve for K. And I do the same thing here, 0.081 equals K times 0.2 squared, and solve for K. And then take the average of all my experiments, and that'll give me my best K. But sometimes, if you're in a test, just finding one will allow you to pick the right answer in a multiple choice, because all the other ones are far away from it. And so that's how we get the final piece, the K, and we have to know, the units of K are such that when multiplied by the concentration dependency, it always gives the rates in molarities per second. One thing I didn't mention here is they have a column called the disappearance of CH3CHO. So that would be minus the change in the concentration of CH3CHO over time. Remember, we would be scaling that by the stoichiometric coefficient, in this case is 1, and that would equal the rate of the reaction. So another way to label this column here is just call that the rate of the reaction, because the rate of appearance or disappearance of any of the products or reactants with the stoichiometric coefficient of 1 equals the rate of the reaction. And we were showing that's true in our last meeting. So I just wanted to point that out. Sometimes they'll have that as in terms of the production rate of a product or the consumption rate of a reactant, but that's always related to the overall rate. Now, when the stoichiometric coefficient is 1, then it equals. But if it's not 1, then you have to take their data and you have to transfer it into another column for the rate of the reaction. Okay? This happens to, equal the rate of the reaction. But if there's a stoichiometric coefficient involved, then you're going to have to scale these numbers accordingly. And when I say accordingly, I mean according to that generalized rate equation for average rates that we talked about last time. Yeah, this one. Okay, so the overall rate of the reaction equals the rate of consumption of a reactant A when little a, the stoichiometric coefficient is 1. If it's not, if it's 2, 3, 4, 5, then I got to make another column to calculate the rate of the reaction in terms of what I'm given using the stoichiometric coefficient. And so I think there's a couple examples of doing that in your homework. So that's it in theory. And right now I'd like to just maybe take a look at some of the homework problems, unless you guys have a question about something. Anybody? Should we go to the homework?
I had one question. It was on slide 20, where you said that particular reaction was second order, but then when solving for K, you said the units would be meter per second. Would it not be
Yeah, if I
second
said K had
one?
units of meters per second, I'd be wrong.
Oh, okay.
The rate has to have units of molarities per second always, and K changes units to make that so. So if
I said meters, I meant molarity, but I
Yeah.
said meters and I meant molarity. I apologize, but I thought it would be 1 for molarity times seconds.
Yeah, I'll show
If
you
it's
what it
second
is.
order.
Yeah, I'll show you what it is right now. So if it's second order, then this X would be 2, right?
Okay.
And we know that the rate always has to have units of molarities per second. And so K's units have to be, well, something per second. And I know that this concentration has units of molarity squared. So the units are going to be squared from this term. So that means I'm going to need a molarity down here to cancel with one of those to make sure that I have one on the top. So the units for K would be, and I think you said this, 1 over seconds times molarity.
Okay, that makes sense. Thank you.
Yeah, sure, anytime. All right, any other questions before we take a look at the homework, or we could do anything you guys want?
Homework.
All right, homework it is.
Homework.
Okay, let me get rid of that. Go here. Home. So the first homework is kinetics right here. There's 27 problems. And we took a look at the first 2 last time. Let's move this over. And we saw how to use that, the average rate equation with the deltas to relate the rates of change of any reactants and products to the overall rate of the reaction. So we took a quick look at questions 1 and 2 last time. And then we stopped at 3 because we haven't really talked about that material yet. But now I think most of you could probably read this and get the right answer. So we're considering this reaction. Now, as soon as you write down a reaction on a piece of paper, you've defined what are reactants and products. And so that's what they've done. And now they ask you, what is a possible rate law for this reaction? Does anybody, is this first one possible?
Yes.
Yeah, where X is to the first order. How about the second?
No.
No, that's the right answer. Why not?
It's a product.
No, right.
Yeah, that's right. It's a product. And rate laws deal with initials. So there is the concentration of products initially are always going to be 0. And rate laws only determine how the initial concentration of reactants affect rate. That's what a rate law is. So that knocks out the next one. The next one has a Y, that's no good in the next one. So, all right. Number 4, consider the following rate law. How are the exponents n and m determined? Don't even look at this down here. Don't even look at the answers. How are n and m and k, for that matter, determined?
The
By
concentration.
experiment?
Yeah, that's right. Both of you guys are right. By experiments and the concentrations that you set and relate to what the rate is in that experiment. Yep. That's the only way to determine K, N, and M from experimental data. You can't look at the stoichiometric coefficients in a balanced chemical reaction to determine the N and M or the power dependencies of concentration of the reactants on the rate. You need experimental data. All right. Now we get to some examples of what we were playing around with a little bit. So it says in this question 5, the following data were obtained for this reaction of NO with O2. Concentrations are in molecules per cubic centimeters. So it's molecules per volume. It's kind of like a rate, but now that, they're going back to using molecules instead of molarity. But it's okay if you want to change the units. And they give us this, they tell us how the initial rate changes with concentrations of the 2 reactants. We know the form of this rate law. It's going to look like this one down here, where X and Y are not determined. So I looked through the different experiments, 1, 2, 3, 4, 5 experiments. I see experiment 1 and 2 doesn't change oxygen, but it doubles the concentration of NO. So by looking at the results of experiment 1 and 2, which reactant am I trying to find the order of?
O2?
It doesn't change. O2 doesn't change.
Oh, NO.
Yeah, so it's got to be NO, right?
Yes.
Yeah. All right, so I'm going to set up, you can do this either way, I guess. So I double the concentration of NO, I leave O2 fixed. What happens to the rate of the reaction?
It quadruples.
It does. It quadruples. So what type of an effect is that?
Second.
Second order.
Yeah, it's second order. And you can see that That's called the eyeball method, but we can also do that method we were talking about where we take the ratio of rate 1 and rate 2. For rate 1, we get K times the concentration of NO to the X, O2 to the Y in 1. Divide that by 2. We see that the concentration of O2 is the same in 1 and 2, so this drops out, K drops out, and now we have just a math problem. 1 times 10 to the 18, 2 times 10 to the 18, all to the X. And the rate goes up 4 times. So that's a quarter, 1/4, 0.25 equals 0.5 to the X. And we can solve for X using that law of logs method, or I'm sure you can see what X has to be. It has to be 2. So you double 0.5 and you get, or, I'm sorry, you square 0.5 and you get 0.25. So either way, you can see what the answer would be. Now, which experiments would I look at to deduce the effect of O2?
Three and four.
Okay, let's see. 3.
Oh, just kidding. 4 and 5.
Yeah, let me see. I can't write on this thing, so it's hard for me to do it. 1, 2, 3, 4. It changes from, 2 to 3. All right, and for NO, it doesn't change. So NO would drop out like O2 did here, and that's what you want. You want to get rid of the effect of anything but the one that you're trying to determine the order of. And so, you can look at those last two, 4 and 5, right? Let's see, is there any other ones? I could look at 1 and 4, right? That's a double effect. If I look at experiment 1 compared to 4, I see the concentration of NO doesn't change, but O2 doubles. Is that correct?
Yes.
Yes.
Okay. What happens to the rate?
Doubles as well.
It doubles. So what's the order for NO?
First.
Yeah. So by analyzing, you can do it that way, the eyeball method, the way I just talked you through, or you can do this ratio of rates. You're going to get the same answer. And it doesn't matter whether you use 1 and 4 to do it or 4 and 5. Okay. And you guys should practice doing it different ways, because I think it's not always easy to do it. Like if you picked 4 and 5, it wouldn't be as easy, because when you would divide 4 by 6, it's not a clean multiple.
Where did the 0.25 come from?
Oh, that's just the ratio of R1
Oh.
and R2,
Okay, gotcha.
I think. Yeah, it is. It's 2 divided by 8, or 1 divided by 4, which is 0.25. All righty. Any other questions on that? Okay. Well, I'm just going to take a peek at these other ones, and maybe I can get you started in the right direction. I'm not going to do them for you. I want you to check them out. So for the question 6, it looks very similar. You got some data on a reaction, and they want to know what will the initial rate for this last experiment be? Now, in order to do that, you got to find the rate law, right? And then you can plug it in, plug in these concentrations and the K and calculate the initial rate. So do you guys kind of have an approach for this?
Yeah.
Yeah, okay, good. So you're going to use those first 3 experiments to find the rate law, and the rate law is going to have the form, let me see, of this, for this problem. The rate is going to look like K times the concentration of CH3 CBr to some power times the concentration of OH minus to some power. So you're going to use experiments 1, 2, 3 to first find X and Y, and then you're going to find K. And then for the 4th one, you're just going to plug in the K that you found, the concentrations, and these numbers that you found. And you're going to calculate that rate so you can answer the question mark. Any questions on that?
For that one, is OH to the zeroth order? Is that how it would look if something was to the 0th order? Because OH initial rate doesn't change, even though OH does. From
Oh
1 to
yeah,
3.
yes. I see what you're saying now. So you look at experiment 1 and 3 to deduce the effect of hydroxide, OH minus, the second reactant. So you see in experiment 1 and 3, the concentration of that organic bromide goes from 0.1 molar to 0.1 molar. So it doesn't change. Its effect drops out. Whereas hydroxide goes from 0.1 molar to 0.2 molar, and you see the rate doesn't change. So that means it has no effect. That means, yes, the Y for the hydroxide is 0, no effect on the rate. So the rate law is going to be a little simpler. It's not going to have any effect for hydroxide. You're only going to need to put in this concentration and its power, which you probably can see from 1 and 2. What's the power?
The first order.
Yeah. Yep, you're right. You look at the experiment 1 and 2 over here. You see that the rate doubled. It went from 1 to 2, while the concentration of that organic bromide went from 0.1 molar to 0.2. So it doubled. So when it doubles, the rate doubles. That's first order. So this is a 1 over here. So now all you got to do is find K, because now you have the order CH3 CBr to the 1 power. And now you can find K by just putting in the concentration and the rate for any of those 1, 2, or 3. They should be pretty close, but just one should do to calculate K. And then you can plug that K in for 4. R4 equals K times that to the 1 power, which would be 0.3 for 4. All right, any other questions on that one? Okay, let's see, anything here. For a reaction in which A and B react to form C, the following initial rate. They give you an initial rate of formation of C. They don't give you the overall rate, but that's okay, since that's going to equal, because I have A plus B goes to C, and these are all stoichiometric coefficients of 1, so the rate equals the change in the concentration of C over the change in time to 1. This is the rate of production or formation of C. So the overall rate equals what they're giving you there. So no problem. It's just doing more of the same. Tabulated data below. So in this one, they give you changes of concentration for a whole bunch of things here. But you have to remember about rate laws and what they're all about. They give you the units of rate molarities per second. That's good. And they ask you the experimental rate law is, but they don't give you rate. They give you change in I2 over delta T. So you come back here and you say, oh, look at that. That's got a stoichiometric coefficient of 1. So its rate of production equals the overall rate of the reaction. So they could have just put R in here. So don't let that trick you. This one, again, look at this. This time they give you the rate of disappearance. So you're going to have to use that equation that we were talking about and its stoichiometric coefficient up here to make another column for this problem for the rate of reaction, because this rate needs to be divided by 2 to equal, to equal the rate of the reaction. This is the rate of disappearance of NO. So don't get tricked on that one either, guys. And so forth. So they're going to keep asking you about the same reaction a couple times here. But I think you're in good shape now to go ahead and attack those homeworks. So I'm going to end it there. I'm going to wait till everyone leaves as usual, just in case anyone has a question that they want to ask me. Thanks, guys.
Thank you.
Yep.
Thank you.
Thank you.
Thank you.
Hello, Professor.
Hi.
How you doing?
Good. How you doing, Jerry?
Doing great. How do you pronounce your last name?
Toto.
Toto. All right.
Yeah,
Professor
like the dog in the Wizard of Oz.
Oh yeah, I remember it. Professor Toto. So first of all, I want to apologize for being absent yesterday. The reason why I was absent was because I was having difficulties with my computer and I couldn't get access to Zoom.
Uh-huh.
I was able to contact my cousin who's a tech and he was able to fix that problem for me.
Oh,
But
Jerry, did you get a chance to look at the video we made and post it?
yes, I did look at the video you have on Canvas for the syllabus and all that information for the first day. Was that all you went over on the first day, or